My name is Kulbhushan. I'm a solution architect, and by profession, I'll try to define and design solutions which will help organizations to release or deploy their codes in a faster manner and without compromising on the security and quality of the product. So that's about me, and I would be taking this journey from Docker to container orchestration. And the name of that session, as you can see, it's Kubernetes in action. In this particular session, we are going to discuss how we can deploy applications or containerized application in the production environments. So as per the agenda that we are going to discuss, first of all, we'll try to understand that what Deepti has covered, what are the limitations around that. Then we'll try to see that how or what are the products available in the market to mitigate those limitations. On top of that, as we have discussed, it's Kubernetes in action. So Kubernetes is our product that we are going to discuss in detail. We will try to understand the architecture around Kubernetes, that what exactly the architecture and how exactly Kubernetes will get set up for the production. Then we will have a demonstration the way Deepti has performed it, something similar we'll try to do. So let's start our journey with limitation that we have in Docker, due to which Docker can't be used as a standalone software or a tool to productionize the containerized application. So let's try to understand them one by one, starting with scalability. So as you have seen, Deepti has deployed the containers, container 1, container 2, container 3. But what if traffic start increasing? At present, let's say we have 50 hits per second. Our applications start doing well. We have 100 hits per second. We have 1000 hits per second. So I need a capability to scale my application so that it will take the flow or the traffic and do the desired execution. So scalability is something which is missing in this standalone Docker. Next thing is upgrades and rollbacks. Deepti might not have covered that part for the upgrade to changing the application from one image to the other image. But let's say we have deployed one version of application and now we want to upgrade to the version 2. How that would happen? And when I say how that would happen, that means without having a downtime or an outage for my application. Then if let's say the new version doesn't work, I would like to fall back to the previous version. How I can do that? That's a rollback. So these things are not available in Docker. High availability. How I will ensure that my application is always available for traffic or for the business. It's not going down. So high availability is again missing in the standalone Docker. Another thing is security. Security is very minimal in this standalone Docker. When I would like to maintain traffic, define the policies that what kind of IPs I would like to approve for the internal communication, how I want to approve or allow the traffic which is moving out of my container host. So all these things are missing in Docker. Self-healing. Container is running. That was good. But the application within the container somehow is not running. It's in a hung state. It's showing my application is running, but or my container is running, but application is not running. So how I'm going to fix it? It might happen somewhere very late in the evening or might be early in the morning. So I need something or someone which will try and help me out to self-heal those kind of situations. So that's the another thing which we'll try to identify with the help of container orchestrator, which is not available. Data integrity, how to maintain the data across multiple applications or multiple instances of single application running. How the data would remain intact for us, that's something that we'll try to achieve. And last but not the least, internal load balancing for my application. We have mentioned about scalability, high availability. Best practices always say that we should have a risk distribution. And we should have our scalability to be done in a horizontal manner. So when something is getting expand or scaled horizontally, that means we're going to have multiple instances. Multiple instances are going to have different IPs to get the accessibility. So on top of that IPs or those IPs, we are going to put some internal IP that would allow us to maintain or have the internal load balancing. That's is the another capability that we will discuss in this session, which is missing in Docker. So that these are the couple of limitations. There are few more, but these are the most common that we can easily correlate with our day-to-day work. That if we have to deploy any application in the production, what kind of things that we are trying to identify. So in order to achieve or mitigate these kind of limitations, we use a concept called as container orchestrators. Name Kubernetes. Kubernetes is one of the most prominent and heavily used orchestrator at present in the industry. But again, if you don't have a competition, you will never get something which is best. So that's why there are few alternatives does exist in the industry, starting with a product from the same stable, that is Docker community. We have Docker Swarm. Docker Swarm is a product that could be used on top of Docker and help us out to do the productionization of our container application. Then another very known open source community, that is Apache. They have a product called as Apache Mesos. That is the another product which is available as a container orchestrator. And same way, AWS ECS. AWS is a cloud platform and they do have a service called as ECS, that is Elastic Container Service, which could be used for container orchestration and to deploy the application in the production. Apart from that, Azure does have its own, GCP does have its own, but I'm just giving you the one that are quite popular. And then finally, we have current market leader. Why I'm saying market leader? Because most of the organizations that are currently onboarding to the containerization, they are selecting Kubernetes as their choice or their solution for container orchestration or the productionization of their containerized application. That's why it's being called as a market leader. How those organizations are utilizing the Kubernetes or leveraging the services, that's a separate part that we will cover in the upcoming sessions. But at present, we are going to discuss about the base, that how exactly Kubernetes is available in the industry. So let's move forward. What is Kubernetes? So in a simple term, it's just a theory that Kubernetes is a product. It's a powerful tool which is used to orchestrate, deploy, scale your containerized application in an efficient and faster manner. When you talk about Kubernetes, Kubernetes itself is an entire ecosystem. It has multiple components, multiple resources that would help you out to achieve those capabilities or those functionalities for productionized application or productionize the applications as a container. So when we talk about Kubernetes architecture, at the start, it's nothing but the VMs or the nodes that we have in the system. Like when Deepti has created or installed Docker. So what she did, she has created one server. On top of that server, she has installed a Docker. Then she has performed certain commands. Those commands would help her out to create certain containers. Now, same thing it will take here in Kubernetes also. When we start preparing a Kubernetes setup, which is also called as Kubernetes cluster, the first and foremost thing that we have in the cluster, that is nothing but nodes, or in a simple term, they are being called as container hosts. Why I'm calling them as container hosts? Because ultimately, these are the platforms or these are the locations where your containers are getting created or being running in future. So they are being called as container hosts. They would be hosting the container. So definitely we need something to deploy or to create the containers on these machines. So while configuring a Kubernetes cluster, on every node, that will become a part of your Kubernetes cluster, you're going to deploy or install a running package of CRI. CRI stands for Container Runtime Interface. Docker is again one of the CRI that exists or available in the market and compatible with Kubernetes. Apart from that, there are few more CRIs that Kubernetes is compatible with. They're like Containerd, Cryo, Mirantis Container Engine, and of course Docker Engine. For this particular session, we have selected Cryo as our choice for a CRI. So at the end, it's Cryo who is going to create the containers on these machines. And it is continuously running. That's why you can see that it's running in this motion as well. But we need someone or something who would be coordinating or communicating with this cryo so that instructions would be received. Like earlier, Deepti was running Docker container run. She's providing certain instructions, and based on those instructions, Docker was creating the container. Same way, on every machine, now we need an agent who would be coordinating and helping us out to create the containers with the help of Cryo that we have selected as CRI. That is Kubelet. So this kubelet as an agent would continuously be running on every node within the Kubernetes cluster and help you out to create or delete the containers in a simple term. When you talk about these hosts, and when we talk about Kubernetes as a cluster, so there are nodes which can easily be categorized as two types: control plane nodes or master nodes, and your application nodes or worker nodes. When you say control plane nodes, so these are the nodes which would be managing the entire functionality of cluster. Like we have discussed that we are going to have scalability, high availability, internal load balancing, data integrity, security. So there would be something or someone who is maintaining this all functionalities. That will happen on the container host or the control plane host or control plane nodes. So which node will become as a control plane or which node will act as a worker or an app node? In order to do that, we have another package that we will install on every node. That package is being called as kubeadm. So kubeadm is a package or a software, or it's a simple command line utility which is installed on every node, and it would help us out to create a control plane node or to define or create the worker node within the cluster. In order to create a control plane node, we will use kubeadm, and that process is being called as bootstrapping. So we will bootstrap a cluster with the help of kubeadm. Bootstrap means initialize or start. So when we will initiate this process, what this process will do, this process will start deploying or installing the components for control plane. So when we'll do that, so there are broadly 4 components which will get deployed. First component of control plane is Kube API server. So Kube API server is a component which is used as an entry point to communicate with the cluster. So now for you, cluster is a thing that you would be communicating with. You would be sending instructions to the cluster. You would be receiving response from the cluster. That would happen via this API server. So that is the first component that will get installed or start running inside your control plane node. You are going to create resources for your productionized application within the cluster. And the component which is responsible for creation of those resources, that is called as controller manager. That's the second component. Scheduler. As you can see, we have multiple nodes in the cluster. Which container or which application will get deployed on which node, that particular capability would be managed or defined or decided by the kube scheduler. That okay, this is a requirement, this is the application based on the declaration or the definition. A particular node which is suited for this application would be node A or node B. So that is a kube scheduler who is managing that capability. And finally, we have to store the information about the Kubernetes or the cluster, that how many applications are running, how many instances of application are running, what kind of load balancers we are running, what those terms are that we will discuss as we move forward. So that entire information about the cluster is stored in an NoSQL database etcd. So these four components will create a control plane. And once these four components are successfully started on a particular machine, that machine will now become a control plane. And then it will add couple of add-ons. These add-ons are relevant for maintaining the efficient execution or accessibility of application. There are two essential add-ons that will get added to the system. They are Kube Proxy and Core DNS. So there is a concept in Kubernetes called as service discovery. So Kube Proxy is basically helping to implement that capability to identify which service or which application is running where in a particular or which node it is running in that cluster. The Kube Proxy is helping us out to identify those details. And core DNS, as name suggests, it's an internal domain name server which is running within the Kubernetes and helping us out to access applications within the Kubernetes cluster without IPs, or I should say with domain names. With those domain names will automatically get resolved to the relevant IPs with the help of core DNS. So these are the two essential add-ons which are running on control plane. So once your control plane is ready, so these components would be running on your control plane and this machine would actually become your control plane. And this is the cluster. That's why that big box is coming up, that this is a cluster now which is configured. Now, as generally we know that cluster means multiple nodes. So same way we are going to have multiple nodes in this cluster as well. In that case, we have to maintain the networking across multiple nodes so that different containerized applications running across multiple nodes in the cluster, they can communicate with each other. To achieve that capability, we deploy the another component or another network layer, which is called as CNI. CNI stands for Container Network Interface. Correct? That will get deployed in the system. So in our situation, in our scenario, we have selected Calico as our network interface, which would help us out to deploy a network layer. And that layer would basically help us out to set up or define the communication across nodes for the different services that we would deploy. So when we will deploy this Calico cluster or Calico configuration in our system, there are two more services that will start running. These services are called as Calico Kube Controller. So this Kube Controller or Calico Kube Controller, this is a service which is running again and maintaining the network across cluster. And in order to maintain the network on every node, it will run additional agent on every node to control or make the network available on that node. And that resource is being called as Calico node. So initially, when we have bootstrap the cluster, we have the resources that got added, that is API server, controller manager to create the resources, scheduler to assign the nodes, etcd to maintain the data, API server for cluster communication. For accessing the services or applications running inside the cluster, we use Kube proxy is used to identify the services. Core DNS is used to resolve domain names to the relevant IPs. Cube controller will get deployed, or the Calico Cube controller will get deployed as a CNI, which is used to maintain the network. And to maintain the network, it will deploy edge agent. That agent is called as Calico node. So these are the components that will start running on your control plane once this setup is ready. Now you can see there is another node which is on the right hand side, and I would like to get this node attached to my system. And I would like to expand my cluster. In order to achieve it, what we have to do, we have to generate a capability which is called as join command. That's a command that we can use, that we can simply print. So again, kubeadm is something which is used to print or generate that particular command. This command will contain detail about the API server and a token and a discovery token to allow specific worker node to create the communication or connection with the control plane. So we will generate that command from the control plane. We'll take that command all the way to the worker node or app node, and then we will trigger that command. That is running the join command from that machine. So once we run this command based on the input, that is your API server address, your token, and your discovery token, it will try to create the connection. And once connection is established, this node will get connected with the cluster. And as soon as this node will become a part of cluster, now network needs to be maintained on this node as well. So this Calico will do what? It will create the another agent on this new node, so that network can easily be available on this node as well. And then definitely we have to access the applications on this node as well. That's why kubeproxy will also get deployed on this new node. And this overall setup will now become my Thinknyx cluster. So in this cluster at present, I have a 2-node cluster. I have one node which is a control plane. I have another node that is app node, and it is running. So now before I move forward, I'd like to show you certain points and then we will discuss it. So let me open my system for you. So this is my system. And if I can show you here, kubectl get nodes. So this is a 3-node cluster that we have prepared for you. One is control plane, which is this machine, and we have 2 app nodes, app node 1 and app node 2. Correct? So they are currently configured on this particular system. The way I have shown you, I'm not going to execute it, but I can generate that for you. So we can use kubeadm command to produce the token. So kubeadm token, I want to get the token created, and I would like to get this printed in the form of join command. So this command will broadly use to generate that command that I can easily execute on the other side. So this is a sort of command which is helping us out to connect with the system. And if I'll show you the detailing about these nodes that we have, kubectl get nodes. So these are the 3 nodes. On these 3 nodes, I have Kubernetes 1.28.1 version running. These are the internal IPs. We haven't exposed this cluster for the external traffic. That's why there are no external IPs that we have configured. This is the operating system where for these 3 nodes, this is the kernel version and this is the container runtime. As I have shown you, we have used or decided CRYO as our container runtime. So this is 1.28.0, which is compatible with this version of Kubernetes, which is running on this particular machine. So that way, things are being configured in this particular system. There are certain requirements or basic needs that we have One basic need for the control plane is that you should have minimum 2 GB of RAM and 2 core CPU or 2 vCPUs available on a machine, and only that machine can get converted into a control plane. If it is less than 1 or 2 CPU, it will throw an error for you. So that's my 3-node cluster, which is ready and available for usage. Let's go back to the PPT now. Where's the PPT gone? No. So that's the architectural setup that we have, and now it's up and running. We have a 3-node cluster which is ready. Sorry, before coming to this, now that's how the system would work. And you have seen that I was communicating with the cluster. For communication, I was using the another capability or a utility, that is kubectl, which is basically helping us out to create a connection. That connection is happening with the help of a capability called as kubeconfig, which is which is authenticating and authorizing our request to the respective cluster. So there are multiple objects or resources or components resources that we can create in Kubernetes based on our requirement and our application needs. We would be seeing them in practical, but I'm trying to give you certain names that are most commonly or most generally used in the setup. The first are the common one, starting with namespace. Namespace is basically a virtual boundary within the Kubernetes cluster that would allow you out to manage the resources for a particular team or a particular application in a confined environment to keep it isolated from the other systems, though still it is available for accessibility. So for that, we will create a namespace. Within the namespace, when we have to deploy an application as an highly available application with you defining the scaling, and that application is stateless in nature. Stateless means there is no data that needs to be maintained. Data needs to be there, but it's not a relevant data which is maintained for an application, stateless application. For that kind of requirements, we will deploy an application in the form of an object called as deployment. That deployment will broadly help you out to maintain or create a replica set and maintain multiple instances of same machines or same applications on different nodes across cluster. Those instances are being called as pods. Same way, when you have an application which needs to get deployed on all the nodes within the cluster. That means, let's say if you have 10 nodes in a cluster, an application needs to be deployed on every node. For example, it's a monitoring application which you would like to deploy. So you will use the another object called as daemon set. Then when you have an application which is stateful in nature, for example, databases, Cassandra, Zookeeper, Redis. So or any application which is stateful in nature. For such kind of application, you will choose an object in Kubernetes which is stateful. For batch processing, you will use an object called as job. And for scheduled batch processing, you will use an object called as cron jobs. So all these objects that I have explained, deployment, daemon sets, stateful sets, jobs, or cron jobs, they are at the end creating the application for you. But those applications are of different type or different style. One is a stateless application, which we are deploying with the help of deployment. One is stateful application like databases, which we are deploying with the help of stateful set. One is a batch job, that is job. One is a scheduled batch job, that is cron job. One is like a daemon, it should run on every node for capture some data, that is daemon set. So these are the most common resources that you have. On top of that, Kubernetes further help you out to maintain cloud native applications in the system. It will help you out to segregate application from application properties. So let's say you have an application, that application has certain properties. Generally, properties are of two types, sensitive or non-sensitive. To maintain the sensitive properties, you can use an object called as secret, which will help you out to maintain your passwords, your certificates, your keys, or your any other sensitive information. Then for the non-sensitive information that you have, like you have some URL, some username, which might be non-sensitive or some other properties. For that, you will use config maps. So both are used to maintain the data, but secrets are for the sensitive data, config maps are for the non-sensitive data. Then we discussed about data, how I can maintain the data or how I can make my data persistent. In order to maintain a persistent data within my cluster for my applications, I'll attach or I would like to attach some third-party storages with my application or with my Kubernetes cluster to integrate or to attach something as a storage which is running outside my cluster, and to make it available within the cluster, I use an object that is called as persistent volume. And then to make that persistent volume available with my application, which is running under deployment, daemon set, stateful set, job, or cron job, I'll use another thing which is called as persistent volume claim. So claim is used to attach the persistent volume which is running outside the cluster with your relevant applications which are running inside your cluster. That will help you out to persist your data for the longer run and for the executional purpose. So these are the most commonly used objects that we have in Kubernetes. One key object that is there, that is service. Now, when you talk about this object is broadly used to prepare or create an internal load balancing capability. Where exactly that load balancing capability will help, that we will see in this upcoming demo. But that's where it would broadly help us out. So these are the most common things that we have in the Kubernetes. Apart from that, there are many things to maintain the ecosystem. Like you have access, how you're going to manage the access, how you're going to maintain the roles, how you're going to maintain authentication, authorization, networking policies, security policies, batch capabilities. So you have different objects for that. But these are the most commonly used objects that we generally use in the application, or sorry, in the Kubernetes. So that's one part. Now what we will do, we'll try to deploy the same application that Deepti did. So we already have a cluster running. We already have the definitions available. I would be explaining the definitions first to you. I'll showing you that how I have created the things, and then we will move forward and try to deploy that application. For that, let's go back to my setup. So on the left hand side, you can see that I have different definitions created. So as I was showing you, we have secrets, config maps, persistent volume claims. We have deployment. We have namespace. I tried myself to create couple of resources in Kubernetes and try to create or cast that application in a setup. So you have seen that Dipti has already done that. She has first created the network. So we already have the network in place. So we don't have to deploy the network again. Network is already there. The first thing that we are going to do, we're going to create a namespace. A namespace that would help us out to maintain all our resources for this voting application at a common location or for a common point. So that is this namespace definition. It's very simple. I have defined it that I would like to use Kubernetes API. I would like to create a namespace. I would like to create a namespace with the name this. I can do it with a command line as well. For example, all I have to do is kubectl, please create a namespace. Which namespace I want to create? I want to create a namespace with this particular name. So this method is called as imperative way of giving the instruction. So I'm writing a command line, and that command line would help me out to do the needful. And this method is called as declarative way, in which I'm declaring my requirement. Kubernetes is a set of APIs. So I'm declaring which API I would like to use, which object or the resource I would like to create, and what is the name of that resource. So if I press enter here, or if I run this command, it will create a namespace for me. So instead of doing this, I'll do it with the help of kubectl apply, or before that, I'll just show you kubectl get namespaces. I have a couple of namespaces available. These are the default namespaces which got created when you deploy your cluster. Kube system, which is used for maintaining your resources which are needed for the systems or the clusters functioning. Kube public to deploy the resources which would be available to the external public as an anonymous users. Node lease is used to maintain a sort of heartbeat, which is keep on poking and checking the health of your nodes on which your cluster is sitting. So that if something happens to a node, that information would be quickly captured and being informed to the required stakeholders. And now I'm going to create default means default. If nothing is there, it will always be default. So what I'm going to do, I'm going to deploy my application namespace. Apply. So a new namespace got created for me. This is a new namespace with the name Symcloud in action. It is 6 seconds old. And what I have done, this namespace is my default namespace as well. So kubectl get context. Sorry. So this is my default namespace. On this namespace, you can see over here, I have different services. So one such definition is secret. So I'm going to create a secret which will act as my DB password. This is the encoded value which will get encoded and saved in the system in a sensitive format. So it is not visible to the naked eyes once it's got created. For example, kubectl apply, and I would like to go ahead with the number 10. So this secret got created in this system. So when I type kubectl get secrets, I have a secret with the name DB password. If I describe this secret, with the name, so I don't have any value here. It is just saying it's an 8 wise character. It doesn't have any value defined. Same way, the way I'm going to deploy my application, I have created certain configurational setup for the connectivity, like DB URL, DB user, DB name, Redis host. These are the same components that Deepti has already deployed. But the point here is the images that we are going to use for this, those images are generic. Because let's say if somebody has deployed the Redis as Redis-server or Thinknyx-Redis instead of Redis. So the solution that Deepti has shown you, that solution will not work. It will start throwing an error that not able to find Redis or not able to connect with Redis. Same goes with Postgres. So the images that we are going to use here, these are the generic image and they accept the environment variables or they accept the configurational setups. So these are the values. So my Redis is available on this URL. This is an internal URL within the ecosystem that we have. As we have mentioned that we have core DNS, we have internal resolution available. So this URL will automatically get resolved to some IP. Same way this is the username, this is the password. Also, this is the username, this is the database name, and password is something which is already defined in the secret. So these are the properties. So I have segregated my properties from application. In case of earlier session or the earlier demo, those properties are the part of application. But what I have done or what we have done, we have marked them as a separate part and we are configuring them on the fly, depending that who would like to use or create what kind of or what service with which name. So kubectl apply -f, and what I want to apply, I want to apply number 11. Then the database that I'm going to deploy, that database is very important for me because it contains the data about my results, that how many votes I have received, what kind of votes I have. So for that, I have defined a persistent volume. I'm using a type NFS for persisting my data. For that, I have used AWS EFS as my NFS. It has a restriction as per security, so it is only accessible from my nodes. It is not accessible from anywhere else. So this is my definition, which will bring or make this particular EFS, which is running in AWS, inside my cluster for usage. It is elastic in nature, but out of that, I have defined my capacity as 2 GB, that I'm going to use 2 GB. So I'll create it. kubectl apply and persistent volume. So it will create a persistent volume in my cluster. So if I type kubectl get persistent volume. So this is my persistent volume, which is of size 2 GB, which is available. Available means it is not yet claimed by anyone. For claiming purpose, I have this definition available, which will claim so that we can give it to some application for the usage. I'll show you that as well. But this is the configuration for claim. So kubectl apply, and what I want to apply, persistent volume claim. It will create your claim. And now if I can show you kubectl get persistent volume claim. So I have this claim. And parallelly, if I'll show you persistent volume, which is earlier coming as available, it is now bound. It is bound with a claim available in this namespace with the name database, which is this. So now this claim is available in this particular namespace for usage. So same thing I have defined inside my database configuration for the usage purpose. So that is my database deployment over here. So it's a deployment. Apps, name, in which namespace I would like to deploy, how many replicas I would like to have. At present, I'm not using a stateful set on this, but in a production-like scenario, real-time scenarios, for the databases, you should always have a stateful sets. And then this is my definition that how I would like to create my container. It's an official Postgres application or the image that I'm using. Postgres 13.4, that is the version. This is the name of my container which got created. This is the port on which my container or my application or my Postgres server will listen. It's the same information that Deepti has created, but with some add-on capabilities. And now here, the customizations that we have done. So instead of keeping the information or the properties within the application, we have set it up as an environment variable. So I'm telling that please create an environment variable with the name Postgres password. That password will take the value or refer the value which is available inside the secret. So I'm nowhere hard coding my password. Anybody can keep any password while creating and then use it over here. So that's what I have defined and make it available for the usage. And same way here I have defined the volume that I want my deployment should use to persist my data for my database. So this is the volume, which is this claim. That will create an internal channel for the communication, but that's how the definition would be declared. And then this volume will get attached inside the container with the help of a capability called as volume mounts. Name of that mount is this name and on which path. So basically the Postgres server that you have, it write the data at this location. So now when I deploy this particular application, what this application will do, this application will writing the data on this, but actually data will start getting stored inside the NFS that I've configured externally. So that if something happened to my cluster, my data is still intact outside my cluster and it is safe. I can anytime use that data with some other cluster if required. So allow me to deploy it. kubectl apply 05. So now deployment got created. Deployment is a high level capability. Deployment will not directly maintain the application. Deployment will create another manager underneath, which will ensure the availability of application with the numbers of replicas that you have. Like I have mentioned, my replica is 1. So it will keep on maintaining one replica. For that, it will create a thing called as replica set. And that replica set will create an instance of application called as pod. So kubectl get all. So you can see that I have one deployment. That deployment has one replica set, and that replica set has one pod, which is running, and this is maintaining my database. Same way I have other applications being defined. I'm quickly showing you all the application, then I will do a quick deployment in a faster way. Starting with voting app. So same way, the way it was Yogesh Raheja slash Thinknyx vote colon 1.0. Same way we have this Thinknyx voting app colon this. So we have defined that how we would like to start the application. Correct? Then environment from. So we are not hard coding the Redis host where the votes are being captured. We are picking it up from the config map that we have earlier created in this system. So from here, it will get picked up rather than doing a hard coding within the application. So that's how it would work. And I have defined my resources as well. That this particular application needs maximum how much memory and how many or how much CPU it needs. So I have defined all these things over here from the executional standpoint. Same goes with Redis. For Redis also, I have used an official Redis image that is relevant. Database we have already seen. The way Dipti has done, so this is the result. Now, result is reading from the Postgres. So it needs database URL as well, database user ID as well, database password as well, and database name as well. So that information it is capturing from these two details. This is non-sensitive, that is URL, username, and database name. And this is your sensitive information, that is your database. Nowhere hard coding is done. Everything is maintained as a common location and it's available for usage. Finally, you have worker. Again, worker is customized. It is also, it is talking with the database as well. It is talking with the Redis as well. From Redis, it is fetching the data. And from database, it is inserting the data. So all these informations I have configured over here. And same way, I have the relevant services which are exposing this application. So I have vote application, which will listen internally on 5000. Actual application will listen on 80, like Deepti was using 81 and 80 for that. Node port is how I'm going to expose it as a Kubernetes object. Redis is only exposed for the internal traffic, so that is called as cluster IP, which will listen on this particular port. Same way, database only for the internal access listens on this port. And finally, you have result, which is again for the external traffic. That's why it's a node port and it will listen on this port for the external traffic. Now, when I deploy, so now I can show you that how fast it is. All I have to do is apply dot this. So those things which I have already deployed, they're coming as unchanged. Which are new, they got created. Now, if I can show kubectl get pods or the smallest entity or the application instance which is running. So you can see that I have 5, one database, one Redis, one result, one vote, one worker. And now they are available over the internet as well for the usage that I can show you here. kubectl get services. So I have 4 services. Worker is not exposed. Postgres, Redis, result, vote, and it's all done. Now, if I'll go back and try to access my application. So this is my application, the way we have deployed it. I have already casted a couple of votes to prepare it. So you can see that I'm getting a result. Let this be loaded. So we have 3 votes that we have casted. It is accessible on 31001. At present, it is 100%. If we'll try to get it deployed, so this is the interface for the result, and this is the interface for the cast voting. So that's how same application that we have created, that application got deployed as a containerized application, but in a production-like environment with secrets, config maps, or the properties managed separately, persistent volume managed separately, definitions, and they are generic in nature. These files are also available that we would be sharing with you post this session. And that's it, what I have for this particular session. And I'm just sharing the URL. Sorry for that you can use. Okay, chat is turned off. So that's it, team, that I have for this particular session. And I'm signing off from here. I'm giving the reins back to the Divya now.